Yeah, today I would like to talk to you about AI and digitization in ductile cast iron and how we can improve the analysis of microstructure and fracture in it. I work at Fraunhofer IWM in Freiburg, Germany, and I would like to point out my co-author here, Johannes Rosenberger, who is actually not the co-author of this paper. He did most of the research that is in this paper, so special thanks here to him. Okay, so what did we do and why did we do it? So I'm going to present two topics. The first topic is the larger one. The second topic is only going to be a couple of minutes. We only have preliminary results there. But the first topic is we took a look at the local microstructure parameters from fracture surfaces with image segmentation or deep learning methodologies. And so usually if we have some sort of component with ductile cast iron, we can see we have these nodules in there. And in the component, we can imagine we have a variation of microstructure. Usually what we do is to get an idea of what the microstructure is. We take some sort of sample where we think it's representative, and we make a micrograph here, and then we can run all sorts of analysis, get a distribution function of the particles, and so on and so forth. But we thought it would be a good idea to actually look at the local variation of microstructure, because we all know if we extract a small specimen somewhere else in the component and we fracture it, then there might be a local variation in the microstructure there. And if we want to analyze that, we can't really use this micrograph technique because we would destroy the fracture surface. And we want to get the information of the actual microstructure that was involved in the fracture process. So we wanted to use AI to be able to quantify that and then compare it to what does the so-called nominal microstructure say. The second topic is a bit different. There we tried to use computer tomography to measure crack growth measurement, or to measure crack growth here. Usually in this type of materials, what we do is we construct a crack resistance curve here, J over delta A. And what we do here, what we can do is we do an incremental loading, so-called low blow tests. And then upon load, we blunt the crack tip. And then typical for this type of material is that we get a island-shaped ductile crack growth or stable crack growth at the crack front. And usually what you have to do is you have to break the specimen open, and then an expert looks at the fracture surface and then measures this out. And this is usually very, very subjective. There's a lot of scatter. It's hard to see. But also these very, very short cracks of about 100 micrometers in length, they're actually not able to be quantified by this methodology. And you can easily see that it's desirable to actually get data here to get the J1V value here. So what we wanted to do is use computer tomography to improve this construction of the crack resistance curve. I'm going to go over this modeling of the AI model very quickly due to the time constraints, but basically we have a database of fractured SEB 25 specimens. We have two different types of microstructure. I can refer to them as fine and coarse. It's not important right now, but we took SEM images of 50 times magnification here, annotated them, so we told basically the program what is a graphite particle and what is not. Then we had to patch it, which basically means we just split up the image so we can process it more efficiently. And then we come up with a train validation test data set of about 150 individual images, and then we can train a suitable AI model to detect the particles. Okay, so what you're going to see here is two representative images of microstructures. So you see here a more ductile damaged fracture surface, and you see here more cleavage. And you can see here that the graphite nodules in many cases, or in most of the cases, are captured very, very accurately by the AI model. This is the test data set. So we can assume that the model does its job. And then what we did was we had these segmentation masks. So the model output, we can make binary images from that. White here are the particles. We use scikit image, excuse me, to automatically create or extract these parameters for the particles. So graphite area fraction, particle size, distance, so on and so forth. And of course, what we did was we did the same procedure for the micrographs of the randomly chosen 2D images and wanted to compare them. Okay, so what we see here now is the statistical analysis of three different types of methods. First, I'm going to talk about the circularity of the particles analyzed. So what is the shape of the particle? 1 is ideally round, and 0 is, well, I guess, infinitely long. So we have here the distribution function of the fracture surface analysis. We have the distribution function of the micrograph, and we have something called the micrograph corrected. Now, what is that? Now, you can imagine if you have a micrograph, you just randomly cut the microstructure in a 2D plane. And of course, you don't always cut the particles in the equator. So you don't always get the full diameter of the particles. Actually, on average, you only get, I think, about 79% of the diameter per particle. And there's a paper by Williams et al., I think, that basically can correct this, this distribution function so the particles are basically cut in the diameter. So it basically shifts this distribution function a little bit to the right. So what do we see? Well, we see first off that the average or the median value of the circularity for the fracture surface is about 0.76 here, which is here. We have 0.81, which is a little bit higher in the micrograph, and we have 0.81 here also. So we can see that the typical particle that we analyze on the fracture surface is a little less spherical, so more elongated than what we see on the micrographs. And not only that, we also see that the more extreme elongated particles of a shape factor or a circularity factor of 0.2 to 0.4 are seen here, whereas these things are not detected if you use the micrographs. That makes sense if you think about what we're looking at, because that's the whole point of doing this. If we analyze the fracture surfaces, so we have the particles that are completely revealed because they take place in the fracture process itself. So if we have a weirdly shaped particle here, it's going to be completely observable in its entirety. Whereas if we just do a micrograph, it's very unlikely that we can actually cut this particle with this entire part. And of course, one thing is that this is a little bit different because micrographs are completely random. And on the fracture surface, we not just reveal the particles in their entirety, but we also reveal those particles and clusters that are very, very damage controlling. So the weak spots of the microstructure are revealed here because the crack finds the path of the least resistance. So it's very, very obvious to myself that these very, very elongated large particles are actually seen here because they control the damage. Particle size is very, very similar, at least the logic here. What we see is that the median value here is 55 micrometers in diameter. Here it's 38, and here it's 48. So the typical median fracture surface particle that we analyze is larger than the typical particle that we see on a micrograph. That makes sense again, because by the same explanation, the particles are revealed in their entirety, so we can see the entire particle. And also we see here these little blips here of very, very large particles of 100 micrometers and larger, which are a part of this distribution here on the fracture surface, whereas here on the micrographs, they are pretty much non-existent. Again, makes sense because it's very, very unlikely that we can cut these particles there. Okay, that was the first topic. There's a lot more to talk about that. There's things that you need to consider, that the fracture surface is of course, not flat. That's all a different type of discussion. This is the second part. So we're going to be dealing with computer tomography. And what we did here was, this is preliminary results. So what we tried to do is we scanned a pre-cracked Sharpie specimen with a fatigue pre-crack. You can see here this two different scans and directions. So we have the erosion notch here, and you can see here very, very nicely the fatigue pre-crack. And these dark spots that you see flashing up and down, they're the particles, of course. And so we wanted to see if we can see the fatigue pre-crack and the particles with the same scan first. And the answer to that is yes, it's good. The question is, of course, how well do we see them? How long is the crack? can we see it until the actual crack tip? Because you can imagine, skip here, you can imagine this crack tip gets sharper and sharper. Okay, and the question is, how far can we actually measure this? And that's what we tried to do here for first. So we have the erosion notch, which we measured to about 2.97 millimeters, and then we measured the crack length on both sides with the computer tomography. And what we saw here is that on one side we measured about 4.8 millimeters compared to the optical crack length on the surface that we later then can measure visually. So we're off by about what is that, 500 micrometers difference. 5.2 millimeters. Here we have 5.2 compared to 5.3, so they were only off by about 100 micrometers. So we can see that we can get the crack tip pretty accurately, but not as accurate, in my opinion, as we want it to be, up to about 100 to 500 micrometers in detail. The second question now is, okay, well, we can see the particles, we can analyze them, but how realistically can we quantify them? Here another video again. What we see here is just basically a scan through the specimen again. And what we see in blue and green are the small and medium-sized particles of about 50 to 100 micrometers in diameter. And if you get to red, you can see them sometimes. Those are the very, very large particles that it analyzes, the software. You can see here that this is a pretty big portion with about 55,000 particles that are analyzed. And the question now is, how is the distribution function of the particle diameter of the scan compared to what we did with the 3D corrected micrograph? And I apologize a little bit for the layout here. This is very, very recent results, but I think you'll get the idea. So we have the distribution function of the particle size here for one example. And you can see here that I tried to align this here. So we have 50 micrometers here and 200 micrometers here. And right off the bat, you can see that the distribution function of this scan is very, very different. So we have, it shifted more towards higher or larger particles. So we have the very small particles of smaller than 50 micrometers are not even detected. And we have very, very large particles here of 100 micrometers and larger, which are detected by the algorithm implied here. And if you look at the entire distribution function here, which goes all the way to 500, you can see that this goes on even further. So we have some sort of a quantification bias in here now. And it makes sense if you look at this data right here, because you can see here red are the very, very large particles, which are here. And you can see, though, that common sense tells you this is not really one particle. This is just something that the algorithm thinks it's a cluster of smaller particles, and it sees it as some sort of a network. It sees some sort of connection there. And the same reason why it doesn't see the smaller particles here of 0 to 50 is also because it combines the medium-sized particles, or it combines the smaller particles to medium-sized particles, excuse me. So we're going to have to work a little bit more on the parameters here and maybe do some smaller scans so we can sharpen the algorithm here. That brings me to my summary and outlooks. So for the first part, the local microstructure analysis, it showed that it had excellent accuracy. It allows the local analysis of microstructure involved in the fracture process. We saw that rounder and larger graphite particles are detected. That makes sense because particles are completely revealed in the fracture process. And also the critical particles, they are predominantly involved here as well. The crack growth measurement with computer tomography, it works in the sense that we can see crack and particles at the same time. But we saw that the crack length measured is somewhat satisfactory, but it still can be more accurate. We have about 100 to 500 micrometers accuracy right now. The particle size is overestimated because of the explanation that I just gave. And also smaller particles of 50 micrometers and smaller are not detected yet. And we will have to do further parameter studies to try to improve this. But I'm pretty confident that we will be able to produce better results there. And with that, I would like to conclude and thank you for your attention. I would be happy for a couple of questions.